Swayam Prabha. Digital India. Educated India.
Before tea, we were talking about use of machine learning and why we need to get or make use of machine learning, because formal methods are not able to help. Other methods are rule based methods are very ad hoc, they cannot capture everything, and hence something whatever was under our ability we tried, made some rules and developed this system based on the rules, which were not much scalable. Therefore, we have to look something which can go beyond the capability of human. Now, in human we have capability to think, right? Machine have capability to compute fast, right? That we cannot do that fast. But machine cannot think, we cannot compute fast. Now, this is some way through which we can make the both of them work together and have machine which can think. So, that means which can compute as well as think, hence can go beyond the reach of a human being. So, then there are few quotes about the machine learning. People are like this is again, as I mentioned, there is a big hype of machine learning, and people think that this is a magic bullet which can help and solve everything by itself. Perhaps that is also not the case, but can help up to certain extent, which can take us beyond the limits wherein human can go. So, this quote is from Bill Gates from Microsoft, says a breakthrough in machine learning would be worth 10 Microsofts. So, how important it is. The quote from Tony Tether from DARPA, because internet came out of the DARPA project, American defense. That came as like people say that this was a project which came after Vietnam War. Again, all these wars are creating these infrastructure, and aim was that this is never said, but they say secretly this was the idea that they wanted to profile Vietnamese population and their behavior, and that data has to be transferred way back to US. So, and because at the time US was in war with Vietnam, so then it says that here machine learning is the next internet, because internet was the last revolution, and after internet it would be the machine learning. John Hennessy, president of Stanford University, like here Turing Award winner 2 years ago, significant work on computer architecture. He says that machine learning is the next hot thing that one has to work on. Prabhakar Raghavan from Yahoo Research says web ranking today are mostly a matter of machine learning. The Sun Microsystems CTO says machine learning is going to result in a real revolution. So, these are the some kind of quotes people are using. It says it's like a more hype than the reality, but we are very close. Jerry Young says machine learning is today's discontinuity, and we are moving to the another revolution. So what is the machine learning? Machine learning is automating the automation. Whatever we have done through the writing programs, we have automated the systems, right. That was really a big thing, that you through the development of program you can automate the entire industry, you can automate the services, you can automate many things up to certain extent. However, machine learning is supposed to automate the automation. That means it is supposed to create the programs which are automating the things, right, automating the processes. So, we call this as in say as a macroscopic view, automating the automation. Getting computers to program themselves, you do not need a programmer, it can program by itself. That is the big thing. Though it is not very new, perhaps you people, did you hear about Hemming, who has given the Hemming code, error correcting codes, right. So, I mean Hemming was working in Bell Labs, and that time he was very say fond of programs, and then considering that machine can do everything. One fine day he went to his manager and asked that he needs some more manpower, and what his manager told him is that, look Hemming, you always say that your machine can do everything, then now machine can write the program, why you need to hire programmer, right. If you really believe that machine can do everything, then machine can write the program, because human can write the program. Then why you need to hire new people? So, things are on the process right from those days. Now it is, we are slowly moving towards the reality up to certain extent. It can do up to certain extent some of the things, but may not. So, writing software is the bottleneck now, and writing correct software is the bigger problem that industry is facing, and perhaps this may help to relax this bottleneck up to certain extent. Now, it says that here, rather than writing a program, let the data do work instead. You supply the data, and then let machine use that data and develop its own system to process the information. So, that is the big picture of machine learning that we have. So, now if I compare with the traditional computing system, wherein I have a program, I have some data to operate on, run the program on the data, a machine gives me some output. Machine learning does the other way around. It says that I have some data and I also have output, that what this data is corresponding to, that I have 100 images, all those images are images of human. I have another set of 100 images, they are images of dogs. Now, this should make a program by itself to classify. If I give the next image, then it can tell me whether that image is of human or image is of a dog. So, you have data, you have output, and then computer is supposed to generate a program rather than the output. That is the basic difference between the traditional programming and machine learning. So, it is like here one can say this looks like a magic, right. I have some input output behavior that I have up to certain extent, and then it generate the program. If I have complete input output, in that case it is trivial to generate, right, because I can make the truth table of entire system, that for this input, this is the output, then I can develop the program for that. But we do not have the complete input set. I have very tiny fraction of input set and then generating the program out of that. And it is supposed to work as if I know everything about that and say generate that. For example, if I give a couple of set wherein I give one array and another array, one first array is unsorted array, another array is sorted array, and I like this I give say thousands of examples, it should be able to generate a program that can sort the elements. So, if I give a new array, in that case the after that end result should be the sorted out array, right. So, this is, so I have some input output data, and based on that here it should generate the program. This is not a say looks like a magic, right, not like the traditional programming that we were doing, wherein there is some algorithm that is seed of the system, where we feed some data as a nutrient to that, and then there is a growth of plant, that is the program, right. So, machine learning, if I can say this in nutshell, this apply a prediction function to a feature representation of the image or some another object to get the desired output. Like if I apply a prediction function on this image of apple, in that case it should tell that it is apple. If I apply the prediction function on a image which looks like tomato, it should tell that this is tomato, and then if I say apply the prediction function on the third image, in that case it should say this is a cow, not a dog or cat. So, that is so the machine learning framework has something like here say output. So, I have input and output, and it generates this prediction function that what that function should be, and if I generate a function, in that case I can always create a program to implement that particular function. That is then the trivial part. So, this has two things. One is the training, wherein it give a training set of labeled example, like here the input x1 corresponding output y1, like here as I said, you give say image and then the output label that this is apple or orange or cat or dog or something, or I have some say unsorted array and then the sorted array. So, a training set which has some like the labeled output as a x1 y1 x2 y2 xn yn pairs, and it estimates the prediction function f that I said earlier by minimizing the prediction error on the training set. So, these functions should be, because I have these are not only the sample points in my space, there can be any other input, x can be anything that I can see in the due course of time. So, based on this one, it should generate a function in such a way that it will have least error in the output when it sees some unknown input. At the end, so this is what to extract the prediction function. Once I extracted the prediction function, that is equivalent to like we generate the program, we have written the program, and after that you apply some input and you will check the output, right. Though you have to rely on that, otherwise also we are relying on our computer system, right. How you know that whatever result your computer is giving is correct? Do you have any method to know that? You are running a program, right? So how you know that output of your program is correct? How you cross check that?
Sir, if we check it on a few samples and the logic is correct, then we can.
You know, one example it may be correct, another example it may be incorrect. Like for example, in this case also, if I give the same image, in that case it will correctly predict the output, because it has seen it has already maybe simplest ways I can store that, right? But then if it sees the unknown, in that case there is no match, and it may give something wrong. So in your computer program, when you are having a program, how you say that your program output is correct?
Sample test inputs that we have already know the outputs of.
Okay, so you are saying that through the testing, and testing is never complete, and therefore we can never say anything, right? Mathematically is the formal verification. That's what I said. It's too tough job. It cannot handle the large program. Maybe small tiny program you can say verify. Say for example, if you run a car, a medium sized car, you know how large program it runs? About 200 million lines of code. 200 million, roughly quarter billion lines. That program cannot be handled. And mostly we have trust in the system that my computer is giving me the correct output, right? Because if I know the output, in that case I don't need to run that program, right? So therefore I don't know the output for a given input. And program is not so small so that I can do that computation manually and then can verify. We are just trusting. But there at least there is an algorithm, right? And our algorithm is mathematically correct. Then if there is some error, in that case, that error is in writing the program. Now here I am giving some input and output set, and it is extracting the function. That function may be well suited for that data that I have given as input, but for the rest of the data it may or may not be correct. And that may give us some inaccurate result, and therefore we have to rely on that inaccurate result as well. If some system cannot tolerate that inaccuracy, in that case we cannot use simply. Now we are using security as one of the potential application, wherein we try with our formal methods and rule based systems as much as we can, and want to see that whether we can go something beyond that, because otherwise also I cannot do much. So if it can detect something, in that case, that is some added advantage that we have, and therefore the use of AI is one of the potential candidates to use for uncovering the cyber security threats. So therefore it has to have a testing phase wherein you apply the new input to the extracted function that it has extracted from the given data set, and provide the output y as a function of x. So like here the steps in AI are, you have to train. So like here for training, for example, for these images, I have the various images of apples, tomatoes, cows, dogs, horses, and then now you extract the features of these say images. Like for example, animals have 4 legs, the apple and oranges won't have legs, right? Then you know that what these images are. So they are whether apple, tomato, or cow or something like that. Train the system and then extract the function, and that extracted function f we call as learned model. So, you learn from the given input, and this function f now can be used to test the new image. So, if I get the new image which perhaps you might have seen earlier or you may not have seen earlier, and then now here from this image it extracts the features which it was using earlier to detect this object and apply on the learned model, and through that you can predict that what this image is, whether this image is apple or it is a horse. So, now the one of the thing is you have to extract the features and what those features can be. Now, features can be like a row pixels that I can have, like this photograph. So, this has row pixels. So, all pixel value I can use that as a feature for that particular image, or I can make a histogram. Histogram says that how many pixels are of intensity x, how many pixels are with intensity y, and so on and so forth. So, based on that you can make the histogram, and that histogram can be fed as a feature to detect the object, or there can be many other information one can use. So, where I can get the potential use of this? Now, if I want to compute accurately, like if you want to solve the differential equation and want to find out the solution of the differential equation, perhaps this may not be the potential candidate as of now, maybe tomorrow it may be. Tomorrow perhaps you may give the differential equation and solution and it may start to give you the answer. However, not all. Up to certain extent there are some efforts. Linear equations are easier, differential equations are even people don't know how to solve the higher order partial differential equations. So, that is not completely. There are only efforts. There are efforts in many things, and you can see they can give you some answer, but most of the time those answers are incorrect. Right? Now, the question is, can I live with incorrect answer? That is the question. So, those places where I cannot tolerate the incorrect answer, perhaps AI is not mature to use at this point in time. However, there are applications wherein we can tolerate, and one of the applications that I said, cyber security, wherein this can uncover potentially some unforeseen bugs or security threats that perhaps we are not able to figure out by any other method. Therefore, use of artificial intelligence is one of the potential candidate. Of course, that this is not the magic bullet. So, one of the problem wherein we can use potentially is the classification problem, that I have certain objects and want to classify in various categories, like for example, those objects in terms of whether it is say orange or apple or dog or cat or what is it. So, in terms of that, if I want to classify in couple of categories, perhaps it can give us reasonable result that with pretty high accuracy. Like for example, these are some training data set that I have in two colors. One is blue and another one is red, and you can see that if a new object comes, in that case based on the learning from the previous one, it should place that object in one of the categories, whether it is a class 1 or class 2. And so, now here if the new object comes, if that is pretty close to the blue or the characteristic of blue one, in that case it should classify this as a class 1 object, otherwise it should classify this as a class 2 object. So, now the prediction function gives you the label of the training example, that is very close to x that it has learned from the previous one, right. So, all we need is a distance function from for our input, that with the different inputs what is the distance, nearest distance it has, and perhaps I use the nearest distance, and based on that I can classify. So, the classifier can be a linear or it can be non-linear. Linear means I can draw a straight line between the various objects and can say that the object one side of the line are of class 1 object, another side of the line are the class 2 object, and therefore, these are linearly separable objects. So, and therefore, I can easily draw or construct a function, linear function that can classify this in two different categories, in one side of this straight line as a class 1 and on another side as class 2. Various kind of classifiers people have developed over the year, like your support vector machine, neural networks, naive Bayesian network, logistic regression, randomized forest decision trees, k nearest neighbor, etc., etc. Maybe we do not have much time to discuss more about it, but then I want to give just say a glimpse of this. So, now the question is, when I have large set of methods available to us, we have to choose one. Now, the question is which one I should choose. Then the natural question is which one is the best. Now, can I say that here one technique is better than the another one? If it is, in that case always we will choose that. Why I would choose some inferior one? However, there is no no method which in all respect say perform better than the others, and therefore, some methods are more suitable for one class of applications or one domain of applications, some other methods are more suited for another domain of applications. So, like here for example, in that maybe this is another example. If this picture I want to classify whether this picture what this picture is, and therefore I give the real say answer to this, that it is a motorbike, and therefore, after that it will detect this object, make a boundary of this, and then detect various features of this object, like here it has some wheel, it has some engine, it has some headlight, etc., etc., and based on that it can annotate and can learn. Now, the learning can be of we can vaguely classify in three categories. One can be the unsupervised learning, another one is the supervised learning, and third one is weakly supervised, that means semi supervised kind of learning, wherein we are using some learning features, but then otherwise it is self learning. So, in supervised learning, like here you provide some features, like here if it is a human, may have two eyes, may have nose and chin, etc. So, this is like here based on a generalization of various data that we are gathering, and then getting some features out of it, and learn and train the system, and after that you when you start to test, you can test that. So, now if I generalize the system based on the learning from the various input data, this has following component which can bring some generalization error. One is the bias in the data, that says that how much the average model over the train set differ from the true model. Like true, if I write a program, or maybe mathematically if I write a program and I know that here what would be the output, In that case, now you check the error and then how of all data points are from the real one. In that case, that is the bias. So, that is error due to inaccurate assumptions that we may have, or the simplification of the model we have. Then there are variance. Variance says that here how all points are say off from your model. So, how much model estimated from the different training set differ from each other. Now, this leads to either underfitting or sometimes overfitting. Underfitting is because of the simplification of the model. I can make the model more simplified, like here, for example, if I have human, in that case I detect some of the features, maybe nose, ear, say mouth or chin, etc., etc. So, if I make it more simplified, in that case it gives the high bias error in bias and the low variance, high training error, and then it will because the model is very simplified model, and the test errors are also higher. If it is say model is very complex, that means I have lot of features embedded inside that. In that case, this may say result into overfitting of the model, and in that case you have low bias error and like a high variance error and low training error and the high test error. Like for example, so we have to have a bias and variance trade off. Bias tells us that, say for example, these are the data sets, and if I want to make in the top figure, if I want to make a linear model out of this, that means I want to fit all these data on a straight line wherein I can get the minimum amount of error. So, now if I draw this line, it gives me some error that how much it is off, that is coming from simplistic model, because the linear or straight line is a simplistic model. However, if I want to say put all the data point on the curve, in that case I will get a very high order curve, right, a very high order polynomial, and because of that high order polynomial, in that case you may get error while you are training, but then in while you are testing, in that case it may result into high error, because then that may not, that data point may not fit onto that curve, maybe pretty far off from there. Now, so as I said that as we say, there is no free lunch in the world. If you are gaining something, in that case you have to lose at some other point, and that makes these classifiers also that no classifier is inherently better than others. You need to make a assumption to generalize that, and because of that we are getting some kind of errors. Now, if I do the say classifiers, in that case classifiers I can classify in two categories. One is generative models or discriminative models. Generative models represent the both data and labels. However, discriminative models can learn to directly predict the label from the given data that we have. Now, if it is a generative model, in that case we often make use of the conditional independence and the priors. Like here in discriminative models, most of the time we assume a simple boundary, like here for example the linear line that can say classify this or discriminate in two categories. Example of generative models are like a naive Bayesian or Bayesian network, etc. However, the discriminator model are logistic regression or support vector machine or decision tree, etc., etc. Now in classification problem, what I want that if there are multiple classes, in that case I want to draw the boundary and then say that here the element in region R1 are of one type, element in another region are of different type, and so on and so forth. That can be done by one of the ways. I can use the nearest neighbor, say that here the elements or the which are in near vicinity, perhaps in the same basis or on the transformed basis, will share the properties, and therefore they fall in the same class or same category, and therefore now I can divide my entire data set into couple of say clusters, and use it like any element which fall in that cluster, we give the label that here it will be in that particular say class. Another one is we can use the support vector machine, wherein like here for example I have these data points, and then from these data points I can have a line which is separating these two data points, and these are the two lines which both can classify this in make the separation. But this violet line here, of course this almost like touches some data point in the red set and some data point in the green set. In the similar way, the another line also touches almost like both of them, and then slight error and that can may misclassify your the new test data, and therefore what we want is we want that this separation should be as large as possible, and therefore the sole aim is to maximize the separation, draw the line in such a way that the separation between the different data sets should be maximized. That is the linear support vector machine. In the similar way, we can also, like if the data are distributed like this, you can see that here one data which is in which is say green, that falls in the regime wherein by simple linear classifier I are likely to classify as a red data and or red class, and therefore I may misclassify this, and therefore now rather than having this linear classifier, I can make a rule base or a decision tree wherein I can partition this and make different cuts to this, and we can say that here in one portion all the elements are of the same class, and therefore now by using these cuts whether horizontal or vertical, we can make a complete tree, and that tree can tell me that in which class your data lies, and if now the new element comes, in that case it is likely to detect that in much better way. This is now, so we are going from the linear separation to a kind of non-linear separation. And one of the bigger problem that we are facing, like when we are losing the linearity, in that case how to deal with such kind of data. Like for example this speech recognition, you can see that there are various classes and which are like looks like very much intermixed. A very simple example of this is XOR, right? For XOR operation is not linearly separable. For 0 0 and 1 1 it gives one output, and 0 1 and 1 0 it gives another output, right? Whichever way you make the lines, right, it won't classify these two into. So now what to do with such kind of data which are not linearly separable? And therefore you have to go for the nonlinear functions. And one of the way that people have explored over the years to generate the nonlinear functions is the human brain. That's in a way was explored by people long ago. So, human brain has some input and has some synapse and the neurons, wherein the information from one neuron to another neuron can be propagated in parallel. Other way we can say that we have large number of neurons which are making collective decision for something by coordinating with each other through the signals, and then signals are transferred from one neuron to another neuron in terms of the chemical spikes. The similar way, by inspired by this, the artificial neural network was created, and that can take some inputs, and then those can be added with their relative weights that can tell that the importance of that particular input or particular feature, and then based on that it can say process that information. So, get the weighted sum, and ultimately then so that is corresponding to this human brain system, and then it has to again the neuron has to fire, and then for fire we have to have some kind of activation function that can activate. So, whenever some potential accumulate, action potential comes over here up to certain extent, in that case that fires in the human brain, right. So, to say take care of or to mimic the same, we have a activation function that can be of say many types, like here the sigmoid function or rectilinear function or something like that we can have. Now, if you I just in the interest of time I skip this comparison with human brain, but human brain is very low power kind of system, wherein lot of neurons are working in parallel but consuming very low power. However, computer system consume whole lot of energy in doing this job. So, now the aim is to make the computer system as good and efficient as human brain is. That's the ultimate goal. I don't know when this goal would be achieved, but there are initiative towards that. So, as I said that here these kind of approaches people started way back in 50s and 60s, just after completion after development of an electronic computer which was reliable. And so the perceptron was the simplest system that was developed and can be very useful for classification kind of problem, particularly if it can be classified in two classes or so. Now, so if these are the two different classes, in that case the perceptron can learn to discriminate the two different classes. So, and essentially it started from the Boltzmann machine, and there is a formal theory behind that. Later on we we lost the track of theory and more working on the engineering aspect of the AI or artificial intelligence system. So, the perceptron theorem says that if a linear discriminator exists that can separate the classes without error, the training procedure is guaranteed to find the line or plane that can discriminate these lines. So, if something is linear separable, in that case perceptron or the single neuron system is capable to deal with that kind of classification problem. However, the XOR kind of things are not linearly separable. In that case, simple perceptron cannot help in that. So, then for that you have to go for the multi-level network, wherein I have layers of neurons are collectively learning from the given data input, and so you may have multiple input and multiple output. So, if there are multiple classes, for example, if I want to detect the various kind of attacks, that attacks may be denial of service attack, that may be a malware or ransomware kind of attack, that attack may be SSH scan attack. So, many kind of attacks if I want to classify, in that case it can give you the different or classify attacks in different forms. So, now the question here is, if it is a multi-layer system, you have some input layer, some hidden layer and some output layers. Output layers are the layers which is input layer is equal to the input features that I have. That input feature, like for example in an image, it can be the number of pixels. Output layer is equal to the number of classes that we have, and then there are hidden layers in between. And now the question is how to determine the weights of various edges that I have here. Now, to determine these weights, what one can do is, in this network, first you pick the weights randomly. Take any random number that you can. Of course, if I pick the weight randomly, in that case it will say it may classify horse as apple, perhaps horse is not apple, right. Now I know that there is an error, and because this is supervised learning, I am feeding that this is an apple, not a horse, and therefore it generates the error vector out of it, and then feed that back this network, and say now when I feed it back, what it does is it tries to minimize the error. So that means it has to adjust weights in such a way that the total error in the network can be minimized. Now I minimize the error and then set this one, say weight, and again I apply the new input. So now for all training epoch, in one epoch, say for example I give a set of data, I give that, accumulate the error, based on that you try to back propagate and say that here what should be the error gradient I have, try to minimize that error as much as we can, and then you based on that you again apply the new set. So for all input output training set, using input compute the output in the forward direction, compare the computed output with the trained training output that you have so far. Now adapt the weights in the backward way to improve the output. And how I can improve the output? I can improve the output by reducing the error, right. That is the sole aim that we have. So incrementally you keep on learning. So and then now the question is how long I keep learning. If I get the new image or say new data, in that case again I will apply some input. Perhaps it may classify that as a correct, or may classify that as incorrect, and therefore if it classify incorrect, in that case what to do? I have to learn it again, right. So keep on adjusting that. So when I get to a point wherein I have reasonable accuracy, in that case I should stop. I don't want to go beyond that. If you are going beyond, then again there is a risk of overtraining, because then you are getting more say particular to some of the data sets, and that can disrupt. Now here it can attain, perhaps may not attain the global minima in your data set, but can attain the local minima, that is guaranteed. Like for example, if I take this handwritten numeral data set that is there in the NIST data set, these are the grayscale images, and output are the 9 classes, right, 0 to 9. I want to classify, so I have to give the different inputs written by different people, right, because I write 9 in different way than you write 9, right. So then I have to give the variety of the data, so that it can adapt, it can learn that what are the various ways people are writing the numeral 9, and so after that when it sees the new 9, in that case it should classify that correctly. So say for example this is character 5. and in the initial phase you get the say some input, and then after that the output array can get these numbers with the confidence that 90% it is numeral 9, say 50% something. So and now you keep on training this again and again, you will get like at the end it says that the character is numeral 5, and then you are done with this. So now this way I can learn a complex behavior or complex function that any data set represent. And don't forget that aim is to extract the prediction function. That prediction function should be reasonably correct. We cannot guarantee that it is correct all the time, but it should be reasonably correct. In last couple of years we have gone for like a deeper and deeper neural networks where you have many layers, and the number of layers have gone to like 100 layers to 200 layers. So the type of the layer, you can have fully connected layer, convolution layer, recurrent layers, or something like that. Now we are, I mean, as I said, that mostly working on deep learning and more deep learning, but this deep learning become a more bigger buzzword because a lot of money is involved in that. Many companies have invested a lot, and with a hope that something good will come out of it, and let's hope that something good will come out of it. So ML, machine learning, in nutshell I can say that it is like a collection of thousands of machine learning algorithms that we have developed based on our requirement on the domain, etc. And every year we are getting hundreds of new algorithms. Now question is that which algorithm one should use. That is one first big question. If you look at all these machine learning algorithm, they have three components. One is the how to represent this one, second is how to evaluate, and third one is how to optimize. Now representation can be it can be you can make a decision tree, like I said that if the data are distributed, in that case you can make a decision tree, and then based on the decision tree you make a decision, but then the complexity depends on how deep that tree is, because you may need to go to the leaf node, and that much processing you have to do all the time. This can be a set of rules or a logic program that you can write, can be a graphical model like a Bayesian or Markov network or hidden Markov model you can have. There can be a neural network, support vector machine, and a model ensemble. Evaluation metric that we are using can be accuracy, precision, and recall, or the squared error, likelihood, and all these are the kind of evaluation metric that we are using. So accuracy or precision and recall, if you say combine in one, that gives you the F1 score, and the optimization. So then at the end, now you have to optimize your network, right, based on the given data. And now for what I need to optimize, how do I do that optimization? It can be a combinatorial optimization using some greedy search, or it can be a complex optimization using the gradient descent method that we are using most of the time. We want to move towards a direction wherein gradient of error is reducing, so that it can minimize the error. Or this can be a constraint optimization wherein we can formulate an ILP problem, and then the solution of ILP can minimize that. This is about the artificial intelligence or machine learning that can help us in improving the cyber security. I try to convince you that because the development in artificial intelligence can help us in, say uncovering more say cyber security threats which perhaps are we are not able to uncover by any other traditional or conventional methods that we have.